Hi, my name is Justine Harkness, and in this video we'll learn how to evaluate the regioselectivity in anti-Markovnikov reactions. An anti-Markovnikov reaction is one that does not follow Markovnikov's rule. And just as a refresher on Markovnikov, we add hydrogen to the less substituted carbon so that we'll add the nucleophile to the more substituted carbon. And when the nucleophile is added to the more substituted carbon, that gives us the major product of a Markovnikov addition. That's the product that is found most readily after the reaction. Now, in anti-Markovnikov addition, we flip the major and minor products. So in anti-Markovnikov addition, our major product is one where we add the proton to the more substituted carbon and add the nucleophile to the less substituted carbon. So in Markovnikov, this would be the minor product, but with anti-Markovnikov, this is the major product. And to favor anti-Markovnikov addition, we often have to use more specialized pathways. One of those ways to favor anti-Markovnikov is through a radical addition mechanism. Radicals are where we have unpaired electrons, and you'll often see a radical indicated in a reaction as a dot. And there are a few different ways that we can create radicals. One is the presence of peroxide, and that's ROOR, where the R groups can be hydrogens like we see in hydrogen peroxide, or they could be other alkyl groups. The important thing that is distinctive about a peroxide is the presence of this oxygen-oxygen bond. We can also use ultraviolet light, so you can see either UV for ultraviolet, or you sometimes also see HV. Both of those are indicators that you have UV light and hence a radical addition pathway. The other thing you can do to favor anti-Markovnikov is hydroboration. You'll see this as BH3, and this will add a hydrogen and a boron-containing group. And we'll see examples of both of these pathways as we explore this topic further. So let's dig into those examples. So in our first example, we have free radical addition illustrates why anti-Markovnikov addition favors the production of the minor product. Of course, the minor product being where our nucleophile here, which is bromine radical, will add to the less substituted carbon. Now we got to take a look at the radicals that we formed. And if you aren't familiar with radical stability, the really awesome thing about it is it follows the same trends as we see with carbocations, where the more substituted radical is more stable and the less substituted radical is not so stable. So we're going to take a look at the two different radicals that we form and note whenever that bromine adds, it will form a radical on the adjacent carbon in that double bond. So if we first add the radical to our more substituted carbon, notice that the radical that we get is a primary radical. And if we add that bromine to the less substituted carbon, we would get a secondary radical. Now, since more substituted radicals are more stable, the intermediate that is most likely to be found would be this secondary radical, and this would be our major product since it is more stable. Now let's take a look at the product that we would get with just a normal anti-Markovnikov. So instead of having just bromine by itself, we'll look at hydrogen bromide plus an indicator that we have anti-Markovnikov addition. So this ROOR, as soon as we see those two oxygens, this is our peroxide. And it tells us in the question stem that we favor an anti-Markovnikov addition. So an anti-Markovnikov addition, remember that we'll get addition of the nucleophile, our bromine in this case, to the less substituted carbon. and we'll get the addition of the hydrogen to the more substituted carbon. So this would be the major product we would form in an anti-Markovnikov addition. Again, we know it's anti-Markovnikov due to the presence of peroxide. Now let's take a look at another example. We said we'd look at the hydroboration reaction, so let's take a look. So here we are adding BH3, and this is going to add to the double bond. So all of our sigma bonds or single bonds are going to remain intact. So we can draw out just the skeleton of this molecule, just not putting in that double bond. So in our anti-Markovnikov addition, we are going to add our hydrogen to the more substituted carbon such that we can add our nucleophile to the less substituted carbon. So now you should feel more comfortable predicting the products of anti-Markovnikov addition pathways.